After transport, we finally get to this point called deposition. And deposition means to deposit. So all those sediments finally get deposited. So let's watch a quick video on how that actually works. So what we're seeing here is you have the sediments all coming in. All right, we have this coming in from the river. And then as we come into here to the big open basin, we start to, those smaller and larger pieces actually start to fall out of the suspension of the water and actually get deposited on the bottom of the lake or riverbed, wherever it's at. So that's our deposition process. Now, what do you notice about the finer particles? Where are they going? Those that they're flying are basically going farther away. This is a really big idea I want you guys to pick up on today, and that the velocity of water actually dictates how big a stuff it can carry. So the faster water is moving, the bigger stuff it can move. And here's a little bit of scary news for you. Take a little bit of flooding, let's say 6 inches above normal. So you go out on the street, there's 6 inches of water up on the street. If all you have is a 3% downgrade, like this, 6 inches of water is enough to move a parked vehicle. To actually have enough force to push the vehicle down the road. There's a lot of power behind moving water. So when we think about this, there's a lot of sediments that water can move. And the faster it's moving, the bigger stuff it can carry. So what happens is when water slows down, those bigger things, they have to fall out of suspension. The water no longer has the energy to keep them moving. And that's what you're seeing up here. You're seeing these bigger items. As water slows down at speed, we're losing those bigger items, and then the smaller ones keep going farther and farther out. So we actually get this separation based on these particles. I'm going to do my best to kind of explain this here in the next 10 minutes. Take your garden hose. Typical garden hose, right? Turn the water on, you're just holding the hose with no nozzle on. What does the water do? It simply just plops right out the end, right? Okay, but when you put your thumb over the hole, what happens then? Tommy?
It's like, it shoots out farther.
Shoots out farther. Okay, why?
It's tight.
More water's trying to come out.
More water trying to come out of this. Okay, so basically there's this thing in principle of the fluid dynamics, meaning how fluids move. You have to have equal in and equal out. So by restricting the space that water can move through, that means the water now has to move faster to get the same amount of water out as is what's coming in from behind. Does that make sense? We got to keep it all balanced, otherwise you get a big bulge in the hose. So basically by restricting the area, water moves faster. So if you want water to move really fast, you restrict the channel. Make it a very narrow channel, and the water will fly right through it. But if you open up that channel, go the reverse process. Now I've given the water a much larger area to go through. What's going to happen to the velocity? It's going to dramatically slow down. So look at these two bottom pictures. Okay, one thing I want you guys to notice right here in the picture I just zoomed in on. So we have a very restricted channel coming down the mountainside. You guys see that? Right here, we have a very, very narrow channel. And all of a sudden I hit this wide open plain. It's the same thing with the hose. All of a sudden I got water in narrow channels moving super fast, right? And as soon as I hit that open plain, what happens to my velocity? It immediately slows down. Which means, since I've lost that speed, I've lost that ability to carry the really big stuff. So notice, all this right up here in the front all the big stuff. And then as you move out, what do you notice about the particle sizes? They get smaller and smaller. And that's because as I move away, my velocity keeps decreasing, and then those relative sizes start dropping out. So the first thing to fall out are the big boulders. After that, we then get the small pebbles and small gravel. Then we get the sand, then we get silt, and eventually the clay is the last thing to fall out of suspension. Does that make sense? Okay. What you guys are actually looking at here, these two images are actually called alluvial fans. Alluvial fans. Alluvial meaning like water, generated by water. And they call them fans because they actually look like fans. Think about fans that, you know, the V-shaped fans. Okay, so these are called alluvial fans. And again, you can see we have the large particles up front, smaller particles all the way out in the back. So a lot of our river deltas do exactly the same thing. That's what you're kind of seeing here. This is actually a river delta emptying out over time. And notice here these channels. What happens is the water channel actually changes. It actually sways back and forth in the delta over time. Kind of interesting. All right. So now we get into the liquefaction process. Take mud. You guys ever make mud pies before? Anybody do that as a kid? Blend mud because of mud pie? Right. Here's the thing with mud. What's the main ingredient for mud?
Water.
Water. And lots of it, right? Yeah. Okay, so you got water and mostly clay and a little bit of sand. That's basically what mud is. Loose sediments and a lot of water. What happens in lithification is you get this mud, and over time you get layer and layer and layer of more and more mud. So think like a lake bottom, full of mud, really mucky. And you keep getting layer, layer, layer. Well, just like we talked about earlier with what happens within the earth as you go down in terms of pressure. The deeper you go, what happens to the pressure? Increase. So as this mud keeps getting one layer put on top of it after another, what happens to the pressure underneath? Squishes down, right? So what literally happens, it comes out to be about a third of the original size. Right here we have mud that's really thick with water, and it basically goes to the right. It literally becomes squeezed, and all water is squeezed out of it, and what you're left with then is solid rock. So given enough time, that mud squeezes all the water out and basically becomes dried out, and it creates shale. So when you look at shale stones, you can actually see the layers of the mud. It actually will look almost exactly like this. You can actually see the different layers from all that being compacted down. So that's the liquefaction process. Now there's something really kind of important. This is one thing I want to try in the next 10 minutes. So we're going to pause our notes here. I want you guys to go ahead and grab your rock sets and then go back to your desks. This will absorb the water, shale, allow the water to completely run off. And that's all because of pore spaces. So the pore space is literally the open air spaces between the particles. And with shale, because it's so fine grained, remember we're talking about mud and silt and clay, it's very fine grained. As it gets compacted, those fine grains actually fit together very nicely, very tightly. And therefore you have very little pore space. But with sandstone, sandstone has these very large granules. Right? Think about sand, remember we talked about this yesterday, the little tiny sand grains? Those are very large particles. And they're not nice and even shapes. There's lots of these weird open spaces within sandstone. And so sandstone has a lot of open space called pore spaces, and it allows the water to actually seep into the rock. So that's one of those things I want to make sure we talk about today. So here's an example again of sandstone. We're talking about the open pore spaces. And basically, when we talk about cementation, it's literally being glued together. All right, so what we have right here is we have the sand. The water actually has the dissolved silica in it. And as that water dries out, the silica starts to grow and eventually becomes the glue that holds the rock together. Now, when we have sedimentary rock formation, we get a lot of different stuff that takes place. This is one of those huge fundamental. You remember that list I gave you guys, all these different things? Big ideas to take out of the class. You guys remember that? They passed out early in the term. Okay, this is one of those ones that we're going to talk about today. The fact that geology provides insights into past environments. All you gotta do is look at the rocks and it tells you everything you need to know. We're talking about bedding. Bedding is just a flat layer. It's all bedding in. It's a flat layer of rock. But sometimes we can get graded bedding. This is an example of graded bedding right here. I'm going to pass this around for you guys to take a look at. What you'll notice is it alternates between big pieces to small pieces, big pieces to small pieces. And what's really neat is if you actually take a very close look at this, all the pebbles are angled in the same direction. So graded bedding is typically going to take place in a river environment. And what it actually tells you is that the river is changing its flow over time. So with the large pebbles, that tells you we had a really heavy flow. We were flowing fairly fast. And then over time, that flow becomes less, and so we get smaller particles as we go up. In a situation where you have multiple layers, that's talking about a river that's really going through a lot of changes, where we have high flow times and we have low flow times. And this is over hundreds and thousands of years. So this isn't like from one year to the next. This is over many, many years. Notice right down here in this image, you have the pebbles all lined up in the same direction. That tells you the flow. So when you're looking at that rock being passed around, you can actually tell what direction the water was flowing in that area. It's kind of neat. So again, that's some of the information. I did order into the next rock we'll talk about here in a minute. What more I want to talk about? I was actually looking for a rock, but I was supposed to order one, but it got back ordered, and then they told me they didn't have it anymore. But cross-bedding is. Cross-bedding is, again, is an indication that you have a river environment, and it's literally looking at the river head-on. So if you actually were to stay in the middle of a river, and you could sink yourself down and into the rock layer, this is exactly what you would see. This back and forth cross-bedding of layers. So cross-bedding, again, is indicative that we have a river environment.